If you have any experience in writing Python code, then I'm sure you know how to compare strings. Almost certainly you would use this equality operator. After all, it's built-in, ergonomic, fast, and most importantly, it gets the job done. And while all of that is true, would you use this to compare a secret? The ideal answer should have been no, but despite that, most people would go for it without a second thought. By the end of this video, it will hopefully be intuitive enough for you to reconsider your choices. Let's start off by understanding what really happens under the hood when we use this equality operator. From a highly abstract perspective, this is just a fancy wrapper around many internal functions used to compare not only strings but also integers, floats, dictionaries, arrays, and all sorts of objects. But right now we are only interested in strings, so let's have a look at the source code. You can see it's relatively simple. Basically, there are three checks to ensure both arguments are of the same type, both the strings are of the same length, and finally it uses memcompare from the GNU C library to check if the individual bytes in these memory locations are same or not. Let's dig deeper and take a look at how memcompare is implemented in libc. We can see it's just a few lines of code to compare the individual bytes one by one until a mismatch is found. With this found implementation, let's make a pseudo-equivalent Python function which does exactly the same, purely for the sake of convenience. Speaking strictly from a security perspective, some of you may have realized a critical flaw here, but I would like to make it apparent for the rest of you all. Consider this program. Here I create a string of random length in the range of 1 to 100 and fill it with random characters as well. Now that I have no idea what it will be, let's use this as that unknown secret string. Then I create 100 strings, each of increasing length starting from 1. At this point, it's almost certain that if I compare these strings with secret, it will be unequal. But let's do that anyway, and also measure how much time it takes to do this. Here is the result plotted on a graph. Something strange you will notice here is that the graph attains a maxima when the candidate length is correct. Maybe it's a coincidence? What about now? Or now? From each of these figures, we can conclude that for some reason, it takes considerably longer to compare the two strings if they are of the same length. Let's get our attention back to this custom equality method to understand why this happens. Assume that the secret length is 30. Now, for all candidates with length not equal to 30, we would return from here taking some specific amount of time. But for that one candidate whose length is equal to 30, this check would be passed and it would proceed to get its characters compared with secret. The characters may or may not be equal, but in any case, this takes far more computation before returning the result, which causes the extra noticeable delay. So, just by measuring how long it takes to return the result, we could crack the length of the secret. But that isn't a big deal. Let's see if we can leak the individual characters with this timing attack concept. The idea remains the same. We have the length of the secret, so we create a dummy string of the same length and brute force the first character. All cases will be rejected in the first iteration, all except this one, where the first character is genuinely correct. Here, it would survive the first iteration and go on to get its second character compared. Regardless of the outcome in that round, this extra computation will create a delay which we can measure. After we have the timings, we can just sort them and figure out which character took the maximum amount of time, and that is likely to be correct. We can prepend this leak to the dummy string and repeat the process until the entire secret is leaked character by character. Here is a proof of concept script which does exactly that. As you can see, it did not take a lot of effort to leak the entire secret, but I'm sure many of you will still not be convinced. Some of you may argue that this is because of my poor implementation of the equality operator. So I have another proof to demonstrate that the built-in equality operator is also vulnerable to timing attacks. Take a look at these two codes. In both of them, I create a secret string of 1000 random characters. Then I duplicate them and create a mismatch at the nth index. In a timing unsafe function, we expect it to take more and more time as the mismatch moves from the start to the end of the string. On the left, we have my custom implementation, and on the right, we have the built-in operator. And here is the result. Clearly, both look identical. In both of these cases, the time taken by the function has an almost linear dependency on the position of mismatch, thus proving that both are vulnerable to timing attacks. Now, the key takeaway from this video isn't that you can leak passwords from a database with a stopwatch in hand. That is impractical in most situations due to network jitters and a variety of other reasons as well. But at the same time, you should also not rely on the fact that network jitters will save your database from such kinds of attacks. Sure, it's highly improbable for someone to leak information from a database purely by relying on timing attacks, but the ideal way to save yourself isn't to rely on luck, rather to eliminate time from the response entirely. The equality operator, despite being vulnerable to such attacks, should be used for most cases because it's the best thing we have. But for those critical situations where we have sensitive credentials on the line, maybe we should consider using a timing safe function. Also, just in case some of you are wondering how does the time versus mismatch graph looks like for a timing safe function, here is how it does. Completely random and unpredictable, as how it should be. So finally, I will ask you again, would you still use this to compare a secret?